Okay, so yesterday we looked at different parameters under non-ideal conditions. So today we're going to talk about changing conditions. We're going to have some initial conditions, and those are going to change into some final conditions. So to do that, we need to use the ideal gas law. So we're looking at P PV is equal to nRT. That's the initial condition. That's what we're starting with. And then we're going towards final conditions. Okay, with P, V, N, R, T. So this is initial. Final. Now, what's the same between those two equations? What's the same?
The formula?
Well, the formula is different because one's with initial, the other's with final, except for one of them.
Yeah.
Huh?
The gas.
R, exactly. Good. So now we can set them equal to one another. We solve for R here. Now we can set them equal to one another. Okay, so we have initial conditions, final conditions. So now we can talk about what's changing. Now, how many variables are there? 8. So that means you have to know 7 of the 8 to solve for the remaining one. Okay, so let's do a problem. Now, also, if no gas is introduced into the system or taken out, the ends will cancel. Or if the temperature remains constant, it'll cancel out. Well, that'll save you some math stuff. Okay. And most of the time, there's no gas introduced or let out most of the time. So normally we can cancel out the N, but sometimes it's introduced or taken out. Then you have to leave it in. And that's in moles. Okay, so let's do a problem. Okay. So there's no mention of moles. So we're gonna assume it's 1 mole before and after. In other words, no gas leaked out, no gas was introduced. Okay, so we're just gonna substitute in and solve for the temperature. Okay, first thing we need to do is convert C to K. Now C is smaller than K, that means we have to add 273 to get to K. So it's going to be 12.7 plus 273 equals 285.7 K. Okay, so let's solve for final temperature here. If we're solving for T sub F, we can cross multiply and that'll move it onto top. Okay. So we have T sub F equals okay, so let's see, let's do this in steps. Okay, now we're going to solve, we're going to cross multiply the initial temperature. That's going to bring that over here. And then we're going to divide both sides by a piece of I. That means that cancels. Okay. So now we just substitute in the numbers. Okay, so final pressure is going to be the final volume is going to be 18.2 liters. The initial temperature is 285.7 K. The initial pressure was 123 atmospheres. And initial volume was 23.4. So multiply everything on the top, divide by everything on the bottom. Okay, so we're looking at 2 sig figs. That's 1.8 or what? K. I'm going to subtract 273 because we want it in centigrade. So that's going to be oops. So the new temperature inside that balloon is going to be 7 degrees centigrade. A little on the chilly side. Okay, does that make sense? All we're doing is we're taking initial conditions, final conditions, and solving for one of the variables, typically one of the final variables, to find what the final temperature is going to be after everything readjusts itself. Now, next week is 2 dry labs for the whole week on gas laws. Yeah,
You did 180 minus 273.
did I subtract wrong? That's what happens when I didn't use my calculator. Is that what you're trying to tell me? Yeah, 93. Thank you. So, this week I gave you an alternate dry lab. Next week, I'm gonna give you an additional dry lab, which is a simulation. It's a wonderful simulation out of Colorado, where you can actually, on your laptop or tablet, you can actually modify the variables and everything will change right in front of you. It's really kind of cool. So what you can do is that lab, I need to see how the other one's structured. But anyway, I'm gonna introduce that. And it'll be an alternate one, either the whole thing or part of it. But it's really a nice lab. I'll try to put that up sooner than later. Okay, any questions about this? Okay, all right. That's it for gas laws. And I'm surprised we don't do a wet lab here in gas law. This is the only school I've been to where we don't do a wet lab for gas laws. All kinds of stuff we can do for gas law. One thing we did up at Sierra was we had liquid nitrogen. We took a handball, put it in the liquid nitrogen for like 10 minutes, and then tried to bounce it. What do you think happened? Jelly cracked it first. I tried to bounce it and go, bang, cover the whole room, little tiny pieces of handball. Boy, cool. Anyway, there's some other things. We dropped flowers in there, flowers, really cool. Okay, so what we're gonna do now is go into something called electronic configuration. Now, this happened out of quantum mechanics back 150 years ago. No, 120 years ago. During the last century, 1900-ish. And it was an advance off of Bohr's atom. So I'm going to now, on this one, it helps to have a periodic table. Where is my periodic table? Okay. Now, what quantum mechanics did, it would allow us to look at things like an electron. electrons can be in different places around the atom, depending on the size of the atom, how many electrons are there. And you can use that to introduce bonding, ion stability, all kinds of stuff. It's a very useful tool. Okay, so let's review Bohr. Because we're going to build on Bohr. Bohr, remember, was the physicist that came up with the idea of the electrons are like a solar system inside the atom, with the nucleus being in the middle. And the electrons revolved around the nucleus. Now, there's some issues with that model, and that's why we came to the quantum mechanical model. But let's look at and in Bohr's model, the innermost orbital is the most stable. But because it's small, it can only fit 2 electrons maximum. And then we went out. The next one out was 8 electrons, and it kept building from there. Okay, let's look at something like lithium. Now, lithium is on the left side, and it's got 3 electrons. So let's see where those electrons go. Now, one thing about Bohr's model is that he put too many electrons in the second orbital out. So what we did is we subdivided that one into 4 suborbitals. So really, there are 4 here. Perfectly drawn, I might add. And each suborbital has 2 electrons in it. That's how we end up with 8. 8 divided by 4 is 2, okay? All right, so we have 3 electrons for lithium. Now, the way electrons are set up is it goes to the most stable place first, which is the innermost electron orbital. So that means we have 2 electrons here. And how many electrons is left over? 3 minus 2, 1 electron left over. So it's going to go over here. Now, of those 4 suborbitals, not all are equal. The first one is more equal than the other 3. So it will fill first. It's a little more stable than the other 3. Okay, so that's what the electronic configuration for lithium is. Now, I want to characterize that. How many electrons does uranium have? On the very bottom.
92.
92 electrons. Can you imagine how tedious that's going to be with all these circles? So there's a shorthand way of doing it. So what we're going to do is the first orbital is that really super stable one. We're going to call that shell 1. The next one out is, guess what? Shell number what? 2. However, 2 is subdivided. So we have something called a subshell. How many subshells are in shell number 2? Based on the lines, the circles I drew up here. 2. There is something called S and P. Subshell S, subshell P. Okay, how many orbitals does subshell P have? Remember, there are 8 possibilities, so we subdivided it into 4 parts. One is more stable than the other one. Well, we've got 1 for the S, 3 for the P's, and those are called orbitals, as opposed to orbits. Bohr call these orbits. Quantum mechanics calls it orbitals. Okay. So let's put those 3 electrons from lithium into this configuration. Okay, so we had 2 electrons here. We had 1 left over, and that's going to go the more stable of the 2, the S and P, which is going to be here. So to write that out in a compact form, we're going to write it like this. Okay, so this is the shell. That's the subshell. That's the number of electrons in the subshell. And notice in shell number 1, there's an S there. Because of the suborbitals, S is more stable than anything. Well, it doesn't have anything else, so it's just plain old S. After that, it's subdivided even more. Okay, I'm actually sleeping now, by the way, at night. I woke up this morning refreshed. I couldn't believe it. Now I got up early to play bridge, and I was going like, this is weird. I can walk in a straight line. Oh, you have no idea what it's like to get away from that cough. Oh, I felt trapped. You know? So I know that has a lot to do with electronic configuration. I just wanted to throw that in. Okay, so this is the electronic configuration for lithium. 1s2, 2s1. Now, you need lots of practice on this. Because it gets kind of wild when we get up into the big numbers. Okay, so are there any questions about this? Probably have a lot of weirdness about this. Huh? Not a big portion, but a portion, yeah. Basically, I'll give you 2 questions on it. I don't know how many. I haven't done the test yet. I've got to get that done. She's leaving early, so she can just take the test. So, okay, but it'll make more sense as we do more. Yeah.
So the 1 and 2, they have to put the shell. And then.
Yeah, the first
subshell.
Yeah.
So
Yeah.
2 and subshell 1, 1 subshell 2.
And the shell, notice there's 4 subshell total, S, P, D, and N. Depending on the complexity of them.
So when we get into the higher numbers, the majority of them are gonna be in subshell 1. Because that's the,
Right. No, it's only 2.
what about for like uranium, you said?
Yeah, but you really got 1 and 2. But then it's got 90 more electrons in it.
So it's the
Oh,
majority.
yeah, yeah. Electron configuration range, you'll see it's about that long. Okay, so let's do another one. Let's do I don't know, let's do oxygen. Okay, how many total electrons are in oxygen? How many? 8. So we're gonna account for all 8 electrons. Okay, so we always start with the most stable shell, which is 1. And that's at 1s. How many can fit in the 1s shell? 2. Okay, that takes care of 2 of the 8. 6 more to place. Okay, the next one out is 2, and it's got 2 subshells, P and S. S is more stable than P, so it's going to fill first. And that's taking care of 4 of them now. We have 4 more to go. How many can fit in the 2P subshell? Remember, there are 3 parts. 2 times, how many parts? There are 3 parts. Each part can hold 2 electrons. So you can put 6 electrons in that P subshell. So we're going to go like this. Now remember, there are 3 orbitals. We're going to call them P sub x because it goes along the x-axis, y-axis, and z-axis.
So what does P stand?
Huh?
What does P represent? So just a.
P is the next. Okay, in shell 2, we have 2 subshells, S and P. P, however, has 3 subshells.
Well, S only has 2 subshells and P has 3 subshells.
Are those elements that you're talking about, S and P?
No. Those are just electron places. So let's go over this again. Okay, so remember, P can hold 6 electrons total. Total. But we only have 4 left. Okay, so those 4 left are distributed between the 3 orbitals or parts of the P shell. Okay, we're going to put 1 in each one. That takes care of the one along the x-axis, y-axis, and the z-axis. So it's going to be 1, 1, 1, and we have 1 more left over. So now we're going to pair it up in the x.
So the first orbital has 1 shell, the second orbital has 2 subshells, and then the third orbital has 3 subshells. So it just continuously builds.
Yes.
Yeah.
And then it
And
goes,
you always wanna
and then it
stack
goes to
on
4
the inner,
subshells.
because yeah, you always want to stack in the inner because it's the. That's why you put the 2 in that. Yeah.
Okay. So with that thought, you're on a good track there. So, okay, so how are we going to write this? Okay, so this is the electronic configuration view. So we're going to write this. And we're going to put the X, Y, Z together when we do the configuration view. That's going to be 1s2, 2s2, 2p4. Now that's the configuration view. We're lumping the X, Y, Z together, knowing that there are 3 orbitals there in that P, but we lumped them all together for the configuration view. There's another view. That's the orbital view. Okay, to do that, we're going to substitute indicating an orbital. So the 1s has got 2 electrons in there. Those arrows indicate electrons. Notice I have them going in opposite directions. Now, electrons have a magnetic component to it. They're like tiny little magnets. This is why some metals are magnetic and some are not. It has to do with electrons in there, how they align. Okay, when you have two magnets together and you're just having your hand without doing anything, how do they align? There's one way they align, and the other way you have to force it. How do they align without doing anything? Huh?
Heaviest in the middle.
Yeah, I'm not looking for that though, but yes. North and south attract each other. South and north attract each other. So when you have the two magnets together like this, they're really like this. And they attract. If they're like this, they repel. So if you're going to jam two electrons in the same orbital, which do you think is more stable? Like this or like this? Exactly. Opposite. That's why the arrows indicate they're opposite up there. The first thing you do is put one electron in each of the suborbitals, and then any left over, then you start pairing them up. And you pair them up opposite again. Okay, so all right, so that takes care of it, and then there's 2s. We have two electrons in there as well. And then we have the p part. Now, how many orbitals are in p? 3. And we have 4 electrons to share. Oops. One, 2, 3, 4. So that's the orbital view for oxygen. Now, the orbital view gives you more information yet. It's the most detailed of them all. Okay, is everyone okay? I didn't say you're a genius yet. Is everyone okay with what we've done so far?
So what happens when it's getting small? I'm so confused. Ah. I get with the first shell and the second shell, so, because we were talking about like, there's two subshells, subshell S and subshell P. Subshell S starts with a 1. And then it goes on,
The first shell
the first shell
starts with 1.
with 1, the first shell starts,
And then within that first shell,
there's 2.
there's 2 electrons.
So,
Within the first shell, there is 1 subshell, that's the S.
okay,
All right, in other words, 1 orbital, S. Okay. Level 2, shell 2, we've got 2 subshells.
okay,
First one is always S. Second one's always P. Well, I shouldn't say always P. First one is always S. And then the second one with the smaller atoms is always second. Okay, so we have an S and a P within
the second, okay.
Okay, yeah.
Like the outermost shell and then it goes in.
No, it goes,
In.
1s is the innermost,
In.
because that's the most stable. So it fills first. Okay, yeah.
So. Subshell P X has 2. Subshell P Y has 1, and then subshell
Z,
P V has 1.
exactly. Now, when we get higher up, they don't align on the axes like P does. P is really clean cut. X, Y, Z. When we get into the D's and the F's, they're crazy looking.
What if nitrogen? 7 electrons, which is when 1 from the subshell T Y, and then leave Z blank?
Yeah, not blank, only 1, because you put 1 in each one first. And then the leftovers, then you start pairing them up.
You put 1 shell, and anything remaining, you
You start pairing them up.
go back to the inner. Parent?
We go back to the start of the P's. Yeah, exactly that though.
So if it was 6, like, carbon, then it'd be one per.
One.
and then one paired up.
Okay.
Now, carbon is an exception. There are many exceptions on here. I'm not going to teach you any of the exceptions because it's out of the scope of this class, but there are some exceptions. Has to do with stability rules and okay. All right, so the orbital view for oxygen is one at the bottom. And there's always three places. Sometimes they're empty. You still have to represent it though, as a possibility. Because if you excite an electron, it's going to go to where the empty orbitals. Okay, that's why you have to always represent empty ones. Okay, shall we do another one?
Yeah.
Okay, let's do one. What's under nitrogen? P. Okay. So here's P. Got 15 electrons now to deal with. Now I want to show you something before we go on. See these numbers over here? Those are called periods or shells. I like shells better than periods, but you'll see both. When we're talking about electronic configuration, you'll never see periods, it's always shells. Okay, notice on shell 1, we've got hydrogen and helium. Shell 2, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen. So the alignment on the periodic table goes with the electronic configuration. Okay, if the point is on shell 3, like we're going to see in a minute here with phosphorus, notice it's 1, 2, 3. So that's shell 3. So our rightmost notation on the electronic configuration is going to be 3 something. And then if it's over here, for example, it's going to be 4 something. Now, when we go below here, things get a little trickier. So we're not going to go there yet. In fact, I'm not sure I can go there today. I don't know. Okay, all right, we're going to do P. All right, so P's got, was it 15 electrons? Oh, and one other thing, all the superscripts have to add up to that number there. So we've got 4 plus 2 plus 2 is 8. So the superscripts and the total number of electrons have to be equal. Because we're just accounting for all those electrons. And we're writing this configuration for the last one. And if you take away an electron, it'll be the second one down, third one down, etc. But the one we're writing for is the electron that we put in last. Okay? All right. So you're going to see a pattern here. And it's important to see the pattern. Notice we always start off with 1s. That means we have 13 more electrons to go. We're going to go 2s. And the S's and P's are both in shell number 2. How many total can we have in P? Okay, that takes care of 10. What's after shell 2? Shell 3. Start with the S again. 2. How many are left over? 3. So we have 10, 2 and 3 is 15. So that's electronic electronic configuration, easy for me to say. Phosphorus, yeah,
Three parts or is it 4 parts?
3.
So each shell has its own shell and then,
Each shell
Three
is made up of
subshells.
subshells.
yeah, okay,
So at level 3, there's 2 subshells,
yeah.
okay? It's always an S, and then next comes P, after that comes D, and then F, when we get like uranium.
Okay. So does it stay at 3 subshells or does it continue?
Well, it depends where we're going here.
Yeah,
All right, so that's the electronic configuration.
Can you like really explain, so I kind of got lost for a minute, like 4, 6, and 3, can you like explain what they're on? They're forward. So
Well, we're
Yeah.
adding electrons as we go.
correct by 2.
And we start, yes, and we start at 1, we rapidly fill up 1 because I only have 2. Yeah, and we got to go to 2 and then start filling up S and Ps. And we've filled them up. Now we got to go to the next one, which is the 3 level. So we start all over again with the S and the Ps.
Okay, I get it, and then 3. Okay, keep going.
Yeah, and now after this, things get more interesting. Okay, so let's do the orbital configuration for this. All right, so we've got, do you see the pattern though? It's a pattern. Now I'm going to tell you something in a few minutes that one of my student tutors taught my class. And this is a long time ago. Now, this woman was magic. She had 3 kids. She was single, worked full-time, and got A's in all 3 of the classes I taught up in Washington. A's, and not just A's, great A's. I can use her test as a key, and sometimes her tests were better than my keys. They were neatly done. She was something else. Anyway, this is the way, and she had the 3 kids, and they were, I think the oldest was 10 or something like that. So she had some, yeah, stair steppers. So she was used to telling stories. So she taught my students how to do this electronic configuration with a story. It was a voyage on the periodic table. Okay? All right, so let me show you how she did it. Okay, now remember the 1s, 2s, 2p, 3s, 3p. Go to our periodic table. And first thing you do is you find your element. Now we're going to take a journey starting at hydrogen to get there. Now this works every single time. No exceptions. Her name was Chris. She was genius. So I've been giving her credit for this for been over a decade. All right, so we're going to go on the little journey now, periodic table. We're going to go along here. And as we go along, we're going to write down the stuff we come across. Well, to start with, we're on shell what? 1. And how far did we go? 2. All right, let's continue on. Now we're on shell number 2. Okay, we went through. Now these are, let me add a quick deal on this. Okay, these are P's. These are S's, including this one here. And these are Ds. And these are Fs. Because you need to know that as we go along the journey. Okay, we're in shell 2 now. We pass through the S electrons. Now we're going over to the P's and we go through all 6 of them. 1, 2, 3, 4, 5, 6. We went through 6 of them. Not done yet. We haven't got to P yet. So now we're going to go to shell 3. We go through the S electrons. And now we go up to P. How far in does P? Into the P's? 3. Did that make sense? Was that easier than understanding what I told you before?
Does that work for all, whatever you're asking for?
Yep,
Oh, so that will teach you where you need to stop.
exactly. So we're looking at phosphorus, so you stop at phosphorus.
And it doesn't go anywhere after these? Or-
Yeah, it does.
But maybe it's asking for P. So yeah, but I'm speaking of the whole thing.
Yeah, it works every time, except for the exceptions, and we're not going to touch on the exceptions. But everything else works great. Yeah, you just go through the blocks. Okay, does that make sense? Yeah. All right. So. Okay, so why don't you do sulfur, S? And use that method. Now, you don't have to use that method if you don't want to. I'm just saying, though, that that's one way she made it simpler for her to tease. That's what tutors call their clients, to tease. I bet you didn't know that. Take out a periodic table. There's a good one in your lab packet.
Yes. You see that? Yeah. Figure that out. So this. So it's a big. Right? Sulfur should be great for humans to be able to read that. Or one more. Or one, that's good. I did find one more than.
6.
There you go, put so. Better? Just one piece.
6. There it is.
Yeah, which kind is that in the habit? About the habit. I just got a little yesterday. Yeah, it was 15 minutes. Yeah. So I got 30. What do you pay for it? Totally? Mine will. Who might, help saving it.
Yes. Okay. I was one from 16. 15,
How does
14, right? This
Yours
is
have it now.
14. And then after that.
It was up to
Michelle.
She have a number two. Yes, is this.
Yeah. And then we're starting. We're starting.
That's the.
So we were in Shell.
I like to track and have everything else on shower. Pressure.
So they-
I ran out of the strips. And the strips cost me. Great. What? So things- So, but I want to track, because I'm faster. I want to watch the fast and sugar.
Six. So.
To all the,
6 hours.
all the cars. Yeah, that's the problem.
No,
Yeah.
so it's a shell. So like, let's say you start off with one shell, right?
Yeah.
You go to the next shell, which is two, you start all over. And then you
Yeah.
have a second shell. So how many shells? Carry 6. The second two. And then
That means.
Six, right? Six, right? So you put three. And then you put two.
For the essence.
For the kids, it's fun.
Well, yeah, sure.
Every-
Every, you go, up, like you're saying, A, B, C,
Yeah.
you have to go back.
Okay.
To,
Yes. And you're
So-
basically- so you- every time-
Who did the journey? No one did the journey. Okay, well, yeah. Yeah, well, let's look at sulfur. Okay, so sulfur is next to P on the periodic table. It's right over here to the right. That means it has one more electron than phosphorus. So instead of P3, it's going to be P4. Otherwise, it's exactly the same. It's going to be 1s2, 2s2, TP3s2, 3p4.
6 if we just keep going.
Okay, so 4N.
The 6, oh, because it ends at AR.
Yeah.
Is that what it means? Because there's 6 on each side. Okay,
That's right.
that makes sense now. It ends
And
at 6.
notice- Notice when the P fills up, it's all the noble gases,
Sixes.
all the noble gases.
Yeah. Oh.
And that configuration is why it's so stable. It's because it's full.
Oh, that makes sense. God, she is a genius. We should figure out that there was only 6, there was 6 P that you can hold on that side and the 2 right there.
Yeah,
Yes.
Yep.
That's great.
But this is.
And then we go back to 4.
Oh, okay.
Oh, yes.
Why?
Two.
Okay, that's one of the, a typical problem I would give on T2, test 2, would correct it. Yeah,
When will we go to D and find it out when we're on the next level of the thing?
okay, so I want to show you what,
The dragon, the dragon.
okay, so as a side note, I want to do uranium for you guys. That's 90, you don't even have to write it down. I just want to show you how complex it can be. Now uranium's at the bottom. It's right here. There's a lot of electrons. All right, so here we go.
What I agree.
Huh?
Which one?
Uranium.
Just to see how far we go with the
Okay,
configuration.
Yeah.
Okay, 5S2. Are we having fun yet? By the way, right now, there's a controversy. There are two periodic tables out there, and this is how they differ, right here. And in 1947, there was a huge debate at the American Chemical Society International Meeting. Half the chemists walked out. Walked out because they didn't believe the one configuration over the other. Had to do with D and F electrons. Okay, so okay, so that's uranium. Kind of wild, huh?
Professor, like when we got to, because I get from the AR, we had 18 electrons, and we end at the 3p6, correct? When we go to the 4 S, I got that on the journey. Then we went to the 3D. Why would we go to 3D?
Right,
We go-
that's a little different. And what my student called it, we're gonna dumb it down by 1. We get to the Fs, that's failing. We're gonna fail down by 2. That's what's weird about it.
Okay,
And it has to do with stability and some other.
okay.
Yeah.
So just,
So the 4 subshells. So. That's 7.
14.
So it goes 3 subshells, 4 subshells, 7 subshells.
It's within the subshell, we have 7 orbitals. Subshell. Okay, so that's how we're doing on time here. 5 o'clock. Okay, I want you to practice this for Monday. Don't go higher than that, because on Monday, I'm going to introduce the D subshell. And we're not going to talk about the F subshell in this class at all. And we're not going to go further down than shell number 4.
Yeah.
So you should feel comfortable doing any of them in shell 4, which includes the Ds as we go across. Okay? So now we're going into dry lab time. Okay, so on our dry lab, I mentioned yesterday, there's an alternative. You can go to files, unit 2, the very top is alternate dry lab 10, and it's more practice on acids and bases. There's going to be more acid-based questions on test 2 than there are on entropy and enthalpy. That's why I want to give you more practice on what we really got meat of the class. Okay, and then next week I'm going to give you additional alternatives, especially the simulator. Simulator's wonderful. And you do a lot of practice on gas theory. Okay, so
Well, to confirm,
any
so
questions?
The Dry Energy Lab,
Okay, for those doing test corrections, try to get those in by midnight. And you'll get half credit that you missed.
It feels like some of them start all over and some of them just get start all over. Maybe.
I got the journey. I got to get them almost, but the journey